So hi, my name is Margalit, and we're going to talk about atomic variables. While they're not radioactive, you probably still don't want to touch them. But the problem is that, as we know, computers are not getting faster for many years. They just multiply. So the only way you can actually get something that's going to be faster these days is basically with parallelism. Now, our problem actually starts from the fact that if we have races between the different threads accessing the same memory location, and one of them is going to write to that location, we have a race. And this race triggers undefined behavior, which means all bets are off, your program is completely broken, you can't do anything with it. And there's actually a really good reason for this undefined behavior. It comes mostly from cache and optimizations, and you don't want to give up on them normally. So the simplest cache architecture we can describe is probably x86 TSO, which basically means that every single CPU we have has its own cache. And if we want to read something, we first check if it's in our cache. And only if it's not there, we're going to read it from the RAM. And the reason is that RAM is actually really slow, at least compared to cache. And when we are going to write the value, we are not going to write it directly to the RAM. We are going to write it to the cache. And at some point in the future, the value should propagate to the RAM. But this means that until it propagates, different CPUs can actually read an older value, a stale value that might not be correct. So this is going to trigger weird behavior. And the other thing is optimizations. Optimizations are awesome. They allow us to write really bad code and actually get decent performance. And sometimes we get bad code just from lowering, so we don't really control it. So if we, for example, have this this matrix summation, where we sum matrix A and matrix B into matrix C. So in terms of mathematical representation, these two codes are the same, since we can do the summation in any kind of order. But from a CPU perspective, there's actually a huge difference in performance because of the way we access the memory. In the first one, we basically jump around everywhere over the columns. And in the rows and then columns, we actually go neatly cell after cell, and everything is in a nice cache line, and we don't have as many jumps. So you really want that kind of optimization, because otherwise things are going to be really slow. So now we're going to see a live demo showing how things break horribly. And we're going to do this with this matrix summation. And we're going to wait until some sentinel value changed. We assumed it right by columns. So by the point that we actually are going to sum the last column, we can safely assume that maybe the value at the first column has already got updated, and we should be able to see it correctly. So we're going to wait for the sentinel value and see how things work or not. So this is the example. We have two threads. One is going to be the summer. And for reasons we'll see, I've decided to actually iterate over the columns and then the rows in the reverse order, trying to get the compiler to do something very specific. And the summer is just going to wait until the last row, or last column 0 is different from 0, changed, and then it can safely probably count the number and see that we get the correct summation. The matrices themselves are going to be initialized with 1s and 2s, just for fun. OK, so we first compile it with GDC and no optimizations whatsoever to see that we actually get correct behavior that we expect. And indeed, we get 30K, which is correct. Everything is fine. So we figure out, yeah, why not? We should trigger optimizations. We want our code to be faster. So let's add O2. And run our code again. And it breaks. So we go back and we figure out, oh, this is his flag. He wanted no finite loops. And what happens is that we have this nice loop over here, the watcher who's waiting, and the compiler says, oh, yeah, you're going to read this value, and it's not going to change between iterations, so we can just read it once and keep the value 0. And then either you end up with an infinite loop, or we are going to just delete the entire thing because there are no infinite loops. So the obvious solution would be volatile, right? The compiler is not allowed to optimize volatile away like this. So it's going to force the compiler to actually load the value every time to make sure that it actually changed and reads the current value. So we go back to our code, compile it, and we add volatile. And great, everything is working. We got our 30K back. But what's going to happen if we're going to crank up the optimizations further? Because everybody loves those 3, right? Oh, boy. That's even worse than what we had earlier. So things are clearly broken here. And trying to understand what happens is that the order that we expected the values to change was basically from bottom to top, left to right. And the compiler decided, no, that's a really horrible way to access the memory. We should probably change it like this. And you should just keep on going with chunks of memories that are neatly packed together to get better performance. And normally this is what you want, because you want to get the best optimization. But for this case, where we expect some kind of ordering, it breaks horribly. So this is where a core.atomic comes to the rescue. This is going to be our solution to figure out how to fix stuff. And it's going to give us defined behavior for races. So we will know what to expect, and it's going to guarantee us sequential consistency. And in order to get this, we're basically going to use atomic load and atomic store over a variable. Now, sequential consistency basically means that you can consider your execution by simple interleaving of the different statements from the different threads. Just take one statement from a thread at a time and execute it, which is very natural. So we're going to see an example. This example is called store buffer. We have X and Y being global memory locations. They are going to be initialized to 0. And then the first thread is going to write 1 to X and read the value of Y. And the other thread is going to write 1 to Y and read the value of X. So under sequential consistency, we could, for example, start from writing 1 to X, and the memory gets updated. And then we can read the value of Y that is currently 0. Next, we are going to write 1 to Y. And finally, we are going to read X, which is 1. And similarly, we can do it in a mirror fashion and get A being 1 and B being 0. Or another execution could be we first write 1 to X, and then 1 to Y, and finally read both ones from the variables. And we can pretty much convince ourselves that under these kind of semantics, we can't read the value 0 for both X and Y, since there is no possible interleaving to get this behavior. So if we go back to our code and replace the writes with atomic store, so we have atomic store over for the C matrix, and the load is going to be atomic load, then now we have defined semantics for the race. And this means that if we go back to our code and compile it with O3, we get the correct result now. So everything is great, except not everything, because we lose performance, a lot of performance. Each sequential consistent access forces us to flush the caches, which means we're basically working on RAM and not cache, and this is slow. And it prevents reordering of statements. It prevents variable hoisting. It prevents many, many kinds of optimizations. So you probably don't want to use it normally unless you have to. The good news is that the C11 memory model, C++ memory model, introduces weaker kinds of accesses, and they are going to be cheaper to use. Races are still going to be defined, so we'll know what to expect, but we have to pay a price. Nothing comes free, and the price we pay is less synchronization. And so the first access is going to be called relaxed, which for some unknown reason is called raw in the D language. Nobody has a really good reason for why it happened. I'm blaming Walter right now. And it provides no synchronization. But what it does provide us is a guarantee that the writes are going to be monotonic over writes to the same variable. But otherwise, it's free for all. So if we initialize x being 0 and then write 1 to x and then 2 to x, and the second thread is going to read the value of x for 2 times, then the second time is guaranteed to be at least bigger or equal to the first time, since we are writing them in ascending order. So the order is kept. But we can't do much with it because there is no synchronization. So we also have release acquire semantics, which allows us to synchronize threads. And specifically, things that happened before the write release happened before the read acquire. So at this point, this thread knows that 1 was written to x, since it happened in its history. And then it writes 1 in a release fashion to y. Then once we read y, this 1 specifically for y, then we must read 1 for x, because we have this kind of synchronization that forces us to know that these kinds of events took place in this order. So now we can look up back to our store buffer example again and consider if we are talking about the release acquire semantics, for example, or the relaxed ones. Can this happen? Can we read 0 for both x and y? And the answer is yes, obviously, since we have no synchronizations. They're not touching the same, they're not reading something that was read by the other thread to force any kind of synchronization. So again, we have this same code. The first thread writes 1 to y and reads x, and the second one writes 1 to x and read y. And we are going to have many iterations until we can actually get this kind of weak behavior that is not guaranteed to happen all the time. And for convenience, I'm just going to use LDC this time. It doesn't really matter, and I'm adding optimizations just to make it faster, but we can get this kind of behavior even without optimizations. So yeah, it's taking a bit now. But yeah, after 11,000 iterations, we actually managed to spot the fact that we read 0 for both values. So it doesn't happen often, but this 1 in a million chance or 1 in 10,000 chance is going to break your code, and you won't even know where to start debugging how things went wrong. Good luck. But you might say, fine, we'll test. Running it many times, as many as required. But the thing is, it's not enough, because you're still limited by the architecture that you're actually running on. So in this case, I'm running it on x86, which actually provides even stronger guarantees than the release acquire statements. But if we're going to run our code on an ARM or PowerPC, then we are going to actually have different kinds of behaviors that we will never be able to exhibit on this machine. Specifically, an example called message passing, where the first thread is going to write this 1 to x, and the second one is going to run 1 to y. And the second thread is going to read the value of y and then read the value of x. And if we read, and we're going to see that on x86 we can't get 1, 0, but on ARM we are actually going to see this, much to our surprise and joy. So this is the x86 machine. It's going to take a while to run. So we'll just put it in the back and move to an ARM machine that I have here. It's going to run the same code. And oh boy, the SSH died. Should have known it's going to happen. Yokit, login. Seriously? Amazing. we'll try it again later. But at this point, we can.
Maybe you have it in the history. You can show us.
Maybe.
Up page up. No.
I think I did clear screen, but I have a recording. So this is going to take a while. I just going to put it in back. BG. And we have ASCII play for a cast that I did prepare on the server just in case. Because you never know if things are going to break like this. It's better to see for fun, but so yeah, it's taking a bit of time. And I think it was 12 seconds to get the result, but the idea is it's going to be rare, even seeing it on ARM. So if anybody thought about running plenty of tests trying to get this weak behavior, good luck. It's not practical. There. So 83,000 iterations. Sorry, 830,000 iterations just to actually see this behavior. So good luck with your testing. Oh, and I should mention, I did try to get this working on a virtual machine of ARM, but it doesn't have to introduce all the weak behavior, so I couldn't reproduce it. I really had to use real hardware. So yeah, testing is not going to cut it, if you ask me. And there's also the fact that you probably don't have alpha machine that can actually get all these kinds of crazy behaviors. Oh, and there was another problem. Current compilers are afraid of optimizing atomics. Just like I'm afraid to touch them, so are they. Yeah. So if we go back to our example, here, I swapped out the sequential consistency access with the cheapest one, the relaxed one, and both for the loads and the stores. And now the compiler is legally allowed to make the optimizations and change the ordering where I'm accessing the variables. So we should have seen the problem, except we don't. The compiler is just afraid. So yeah, you can't even trust your testing to work because maybe the compiler just didn't do the kind of optimizations that's going to break your code in a horrible, horrible way. But you know, maybe, okay, fine, testing is not enough. Maybe we need domain experts. Domain experts surely know what they are doing, right? Hopefully. So this is a short story about Peterson's mutual lock. He proposed it back in 1981, and it assumes sequential consistency access. Which was pretty much everything back then. Now, the question is how to implement this lock in the C11 memory model. So Bratosh-Milewski proposed an implementation for this algorithm. And we can see that it makes use of the release acquire accesses. It also has an exchange statement, which is an atomically read and write, read the previous value and store a current value. And it makes use of everything here. And Dmitry Vuyokov, hopefully I'm pronouncing it correctly, said that, you know, it's not right. This implementation uses both is insufficient and excessive fancies at the same time. It's too weak and too strong at the same time. It's like, it's wrong and wasted. And instead he proposed his own implementation for the algorithm. And Bartosh's response was that I don't have a foreign proof that my code is correct. I believe it to be correct. And for all I know, Dimitri's implementation is also correct, but it's much harder to prove. So yeah. Subsequently, Anthony Williams analyzed both algorithms and concluded that Bratosh's implementation wasn't correct. It was actually wrong. And that Dimitri's implementation is correct. So it could be used in production. But all of these experts agreed on one thing. Anytime you deviate from sequential consistency, you increase the complexity of the problems by orders of magnitude. You're basically asking for trouble. Now, so if domain expert thinks that maybe you should keep your way out of this, you know, maybe sometime in the future somebody's going to find a solution. Like maybe some great, bright computer scientists are going to propose a new kind of logic that we'll be able to finally use to prove the correctness of our algorithms. And you see this back in 2020. These guys did an amazing work. They proposed a new kind of logic. And their case study was this implementation of Peterson's algorithm by Dimitri. So that's top-notch stuff and showing how hard it is that researchers need to actually find and prove the correctness. And it is great. They prove the property about the algorithm. There's only one slight problem. The property that they proved is actually insufficient. They proved, yes. They proved that it cannot be that the two threads are in the critical section at the same time. There's only a slight problem that it doesn't mean that they synchronize between each other. So it's actually broken. So yeah, all is lost, maybe. But this is where my research tries to help and address this problem. And the idea is that verification for weak memory models is notoriously hard. You don't want to do this. It's impractical. People get it wrong all the time, and those are people that are probably smarter than me. So what we'd like to do is verify the correctness of the programs assuming sequential consistency, which is easier to reason about. It's something we've been doing for years. We even have model checkers for that. And if we prove that the program is correct under sequential consistency and some property about this program, we want to actually achieve verification under the weak memory model. And this property is called robustness, which basically means that all the possible behaviors the program could exhibit under the weak memory model are those it would have exhibited under sequential consistency. This means that I can reason about it in terms of sequential consistency, because it's not going to have any kinds of new weird behavior on the weaker memory model. And specifically, we focused on the C11 memory model, which is used by itself or a variation of in C, C++, D, Rust, LVM, whatever. So we need to understand the simple things about how the model is actually being described. So instead of having simple executions interleaved like we saw for sequential consistency, we actually produce execution graphs that describe a specific execution of the program. So this is an example of a graph that we're going to produce for our message passing program. So we start with an initial graph where we have the initialization events of writing zeros to the memory. And then we take a single statement and process it. For example, we're going to write 1 to x. So we create a new event in the graph saying that 1 was written to x, and it happened strictly after in terms of program order after the initialization. And next, when we write 1 to y, again, it happens in terms of program order right after the 1 was written to x. Now, we execute the second thread, and we need to justify a read. We are going to read a value, and we are going to read a value 1. So we need to justify it somehow. And we justify it by the fact that we read the 1 from this event that wrote 1 to y. So we have these read-from relations describing that this is where we read the value from. And next, what we're going to do is basically read the value for x and justify the fact that we read 0 because we read it from the initialization. And what defines the graph is basically execution graph to be consistent is having a set of constraints on top of it. And this, for example, is valid, completely valid under the relaxed semantics. And we also have an implied relation that obviously if we read 0 for x, it must have happened before we wrote 1 to x. I mean, otherwise, how else could we have read it? And the idea is that a graph is sequentially consistent if we can linearize the events. So we can actually get some nice interleaving to get this behavior. Specifically, this is a possible linearization to get this graph. And we don't require more than one. There are possibly more, like we could just swap the initialization events. They don't have defined order between them. But obviously, the graph below is SE inconsistent. We cannot linearize it in any way, since this write has to happen, of 1 to x has to happen before 1 to y, which happens before we are actually able to read 1 to y. But obviously, it happened before we read 0 for x, which had to happen. I mean, we read from an earlier event. So we have this nice cycle that means that it's SE inconsistent, and we cannot get it under the sequential consistent memory model, but we can get it under the C11 relaxed memory semantics. And the idea that we found was basically that we can actually check this with sequential consistent semantics. Since there's a minimal violation that happens at some point. At the start, the graph is SE consistent. So at some point in time, we have a transition that takes us from an SE consistent to an SE inconsistent under the C11 machine. And since this can be reached, is SE consistent, we can actually reach this state with an equivalent sequential consistency machine with its own memory. And the fact is that we can actually track these kinds of properties about the fact that the C11 machine is going to be able to take a step and the SE machine cannot. We can actually track this with robustness information with tracking that adds what kind of steps am I going to be able to take under an SE machine compared to what am I going to be able to take under a C11 machine. And this means that if we go back here, we can actually, this state, as we said, is we are able to get this kind of behavior under sequential consistency. That means there's an SE machine with instrumentation that can reach this state. We recognize that at this point, the SE machine must read the value 1 for x, but the C11 machine can actually read from the initialization. And with this kind of information, we report a robustness violation and the fact that you can't assume that the behaviors are only SE consistent because they're not. So if you're willing to limit yourself to just robust programs, you can actually verify their correctness more easily. And yeah. So we built a tool called Rocker, which is, allows us to statically, automatically check the correctness of simple programs. The programs are written in a toy programming language that simplifies the memory model. You can port it. And we do the verification assuming sequential consistency. And this nice little tool is written in D, for this is a D conference. So at first, we tried it with only the release acquire semantics. And we saw that Peterson's original implementation that assumes sequential consistency obviously breaks when you try to use it with weak memory model. And Brato's implementation was breaking even under release acquire. And Dimitri's implementation is actually going to work under x86. So you might miss it if you try to check for bugs. And we also see that the store buffer can actually produce the weak behavior while the message passing cannot. As we've seen, it's probably still running, or it gave up. I'm not sure. We can check later. But the key fact that is amazing is the fact that the verification time is less than 2 seconds. It's like, I don't need to reason about all this. Just run it through this, and yeah, it's robust or not. And then I can just reason about it a lot more easily. And that's when we added the relaxed semantics. And we found out that Dimitri's implementation isn't actually correct. Yeah, it's amazing. All these smart guys get it wrong, and our tool actually found this automatically without having to reason about. Like, we just wanted to take it as a test case, like, let's see, and oh, it's wrong. Let's see the backtrace. Why is it breaking? And find this silly issue there that's really easy to miss. I mean, if you want, I can take it on offline later and show you how things break there, but it's based on time. So we proposed 2 possible implementations that restore the correctness of Peterson's algorithm for the memory model. And we also see that the store buffer and the message passing both fail. So to conclude, we'll be back at this slide later, but we proved that robustness for C11 is decidable, piece is complete, and basically given a program with C-like 11 atomics and non-atomics, we just feed it to Rocker. Rocker creates verification problems that assume sequential consistency. We can run this all on a sequential consistency machine. We can on x86 machine. It doesn't matter. We don't need the real actual weak hardware. And then we feed it to the spin model checker that just tells us whether the program is robust or not robust. And you can try the tool without having to actually understand the memory model. It's available on GitHub. And just one more thing to show the example first. So, for example, this is the metrics. I don't have support for arrays yet, maybe one day. But this tries to simulate the metrics behavior that we saw earlier. So all the stores in the specific order, load until we actually see the value we expect. That's a wait. And then reading all the values. And if I don't state the kind of access, then it's going to be the weakest possible. So it's either going to be release acquire if I'm going to write in the release acquire mode, or relaxed if it's in the relax mode. And I can go back and run it for all our examples. Let's just run it for the metrics. So if I assume sequential consistency, then release acquired, then yeah, it's fine. But once as we saw, once I change it to the relaxed memory model, then yeah, your code is just going to break. Your assumptions are wrong. Don't do this. And we can also state the kinds of accesses explicitly. So here we have all the writes being released. The wait here is going to be acquire. And if we run this example on the other end, then it's going to be robust, since we do actually have correct synchronization like we should have. How much time?
You got plenty of time, man.
OK. So yeah, we also have the message passing and some other examples. I can actually just run them all and talk about them.
Well, do you want to run your examples and take questions at the same
Yeah.
time? All right. Well, then, should we do the applause first, then? Now, we do actually have a question from Discord to kick things off from Ricky. He says you'll know the context about this. How insane is lock-free concurrent data structures, and why is the answer that it is universe breaking?
I'm sorry, could you repeat it?
How insane is lock-free concurrent data structures, and why is the answer that it is universe breaking?
Because you can't reason about it. Reasoning about lock-free, especially with weak memory, is insane. That's why people just stick to the simple algorithms right now, and getting anything that's harder, it's like, good luck.
So I remember a few years ago, the Microsoft team for the C and C++ compiler, they went over the whole standard library and all the library they publish using similar tools to try to detect errors using weak memory models, and they found two, well, one not so surprising thing and one quite surprising thing, at least to me. The first one is that there are very, very few uses of them over the whole code base, right? Like the fraction of atomic operation that use weaker model than sequential consistency was very few sprinkles here and there, but almost none. And the second one, like a significant portion of them was actually wrong. And the question that I'm asking myself is, like, are those really that useful anymore? Because if in practice you don't need them that much, and in the few cases where you think you need them, like half of the time you actually don't, you get it wrong. And on the other hand, you look at what CPUs are doing, and they seem to be getting better and better and better actually at being sequentially consistent, even though, like, I would have expected the opposite to happen with more cores and stuff like that, but they are getting better. Like, should we just like say as an industry, like those weaker memory model, that was a nice experiment, but let's just stick to sequential consistency?
So I feel that, yeah, unless you know really well what you're doing and try to use all the tools to make sure that you actually write correct code, just stay away from all those relaxed accesses because it's really, really easy to get wrong. There's a question whether the performance penalty is worth it or not, but that's for you to decide if you want to risk correctness versus performance hit. But hey, I get to research this stuff, so I'm doing my PhD over this. So,
I have the mic here.
Yeah.
Is Rocker multi-threaded? Do you trust it's correct?
Oh, that's a very good question. Rocker is actually single-threaded. We execute only a single statement at a time, and it's just like we can do for sequential consistency. We don't care what's the actual architecture that we're actually executing on.
Hello?
Yeah.
Does Rocker take a long time to run, and how do you feed it code to check? And can this be something that can be added to the compiler as a robustness check? Because whenever I've tried to analyze multi-threaded code, it really hurts my brain. And having a program that is guaranteed to be correct to say whether it works or not, I think is going to be, or is a great boon to doing these kinds of programs.
So I did start on trying to write a minimal C2 TPL compiler so that I can actually test things. C is hard to compile and trying to get all those primitives. So it's going to take a lot of work. Another direction I tried was basically creating my own thread sanitizer that checks dynamically for all those kinds of things, but it's still work in progress.
Okay. Does it take a long time to run Rocker?
Rocker itself doesn't take that long. I mean, for the example programs that I'm showing, it was like a couple of seconds. But if you have plenty of memory locations that you add, or more than 5 threads, then yes, things are going to take a long time.
Okay. Because I'm thinking, like, you know, I've added a borrow checker to D, and that turned out to be quite workable.
So yeah, maybe there are optimizations I'm missing. I'm not saying I try to optimize it all the way.
Okay. Well, what I'm thinking is I think it would make a nice addition to a compiler or a language to have something like that. It just sounds pretty cool.
Yeah.
I have one question. Even being single-threaded, how did you prove that your implementation is correct?
So what happens is that as long as we have an SE consistent graph, that means that we can actually achieve this kind of graph under an SE machine, right? Mm-hmm. And an SE machine could simply be thought of as taking a statement from each thread one at a time. And what Rocker does is basically check all the possible executions that you might have for this program. So what happens if I'm running this, and this, or this, and this, and that, and all various orders.
But is this, the proof is based on some formal theory?
Yeah, there is a formal proof that this is correct.
That this sequence, but oh, okay.
If you have an SE inconsistent graph, the program is not robust, then at some point you must have had a point of divergence. And we can identify this point of divergence with the instrumentation.
I would buy that, but...
You can read the paper.
But you have I mean, is your proof mechanized or something like that?
Some of it is mechanized with Coq.
Okay.
So it checks things by doing a combinatorial exhaustive check of all possibilities? Mm-hmm. That's how Rocker works?
Yeah. There's also work, as I've stated, that creating a dynamic one that just checks the branch you're actually executing, but following what could have been. But it's still, as I said, work in progress.
Okay.
Any other questions? Yeah, I just checked Discord. There's nothing there either. Anybody else? No more demos to show off?
I can just talk about the examples, but mostly we can see that.
Oh, that's cool, mate. Oh, hold on, we got a question down here now.
Does the tool show us in what condition it may get that no result? Verbose mode, maybe?
Yeah, there's actually an output from Promela, which is the language spin takes. So for the failures, we have this trail file, and I actually wrote some tracer to help me. And we get this horrible, horrible output that more or less shows what's the order of the instruction it took to get the violation. And I basically just got used to reading this. But yeah, it's obviously not the best option. But making developer tools is hard.
All right. Yeah, I think that'll do for questions time now. So thanks again, man.